It's my great pleasure to introduce the first of two keynotes for this year. Those of you who've come in past years know that we sometimes had more, but we're trying to make it up in quality this time and have fewer, and those will be good. I'm really hard-pressed to not sort of bubble up how excited I am about this. I saw Zilla present this a year ago in a session we were both in that I shared at USAR. This is going to be really good. Sort of just one or two words about Szilárd if you haven't met him. He doesn't admit this anymore, but he used to once be one of us, and then he took door A and exited out into data science, so he's no longer a quant. He's a physicist like many, and he's hiding in beautiful Santa Monica. Who could blame him for that? And is a co-founder and runner of the LA R-Users group, and was sort of influential with some of you of getting the network of user groups started. He had me there a couple of years ago, and it's always a pleasure to see him. What he's doing and what he's going to show you is all out there in the open on GitHub. You can replicate all of that, and it's going to be, I think, quite exciting. So. Of course, we're being live streaming, so I have the great pleasure to now say a swear word. So no bullshit data science. If you're interested in this flavor, I just realized there is also an excellent course offered by jointly between two departments by the University of Washington, and I think that one's called Calling Bullshit in the Age of Big Data. So that's more on methodology. Szilárd is sort of taking the scalpel to some hype. So without further ado, I hope you join me in welcoming Szilárd Pavka.
Thank you so much. I'm so honored to be here at Keynote, and I'm also humbled because Keynote talks are supposed to be inspirational. And there is nothing inspirational usually in my talks, at least not in a positive way. You can see starting with the title. So, and indeed, it seems to be like a running joke about data scientists at this conference, based on one of the previous talks here. So, yes, I've been doing what nowadays is called data science. I've been doing that at the e-commerce company in Santa Monica for the last 11 years. But I come originally from physics, and then I did a little bit of finance about 5 years. I exited in 2006, maybe right in good time, but it was purely by chance. I'm also running the R Meetup in LA. We have this website, datascience.la, and I started teaching machine learning at 2 universities part-time. And of course, nothing here is related to my employer. And I'm pretty sure most of us here in this room have been doing data analysis for a decade or 2 decades. And everyone here have seen this increasing amount of hype in the last number of years with big data, data science, and now artificial intelligence. Nowadays, even a simple logistic regression is like an artificial intelligent bot. And I think it's getting kind of worse. So this is real. So I took an Uber to go to a machine learning conference last year, and the Uber driver was asking me where I'm going, and I told him, and he confessed that he wanted to become a data scientist. So a lot of this hype is about the tools we as data analysts or data scientists are assumed to be using, and these tools have like extraordinary powers. They work with big data and they scale, and everything is so nice. So this talk will be some kind of reality check with precise quantitative measurements on the performance of these tools. And I'm telling you, it's not that rosy. So I will have 2 examples for today. The first example is about big data. So we are collecting more and more data, IoT and all these things, and everyone in the last 10 years is telling us that the way to deal with these huge amounts of data, the only way is buy 100 servers, build a cluster, or rent it on Amazon in the cloud, install Hadoop, or lately Spark, and this is the only way you can deal with such amounts of data. I have a different view. Unfortunately, the tools for data analysis on this scale are not really that easy to use. And what I'm going to argue in this example, in this first example, is that actually most of us would probably not even need these tools. So my main point here in this first example, I know most people here, they already know about this. It might be trivial that for most of us, most of the time, all our data fits in the RAM of one single server. You just need enough memory, and then you can use R or, for God forbid, Python or any of the commercial tools to do your analysis. So how much memory we can get? We can easily get 100 gigs for under $1,000. We can go on Amazon. I've been using this 32 cores, 250 gigs RAM instance for at least 3 years. And now you can even get 2 terabytes on one single server with 128 cores. It looks pretty scary. It looks like this. And this is only $13 per hour. So how big are the data sets that people in like data analysis, data mining, data science are using? The KD Nuggets started more than 10 years ago, like a yearly survey. This used to be run by the data mining community before the term data science existed or has been used. And they've been asking their members every year to tell them what's the biggest data set, what's the largest size they've been working that year. And I put the results together in a GitHub. So there were these yearly surveys. So this would be the cumulative distribution over the sizes on a log scale, the size. And I was wondering of course, how big and then how fast these data set sizes are increasing. I also asked on Twitter. It seems like a lot of people are working with like a gigabyte of data or even less, or maybe a few gigabytes of data. In number of records, typically like 1 million records, and few people are doing, let's say, machine learning on more than 100 million records. And I think also it's, if you don't have big data, don't be ashamed. So it's not always the size matters. So if you, maybe data is not so big, but there are people saying that it's going to get very big soon. So how fast are these data sets increasing? So in the survey, if you fit this kind of simple linear model on the middle of the cumulative distribution function, from the coefficient, you can figure out that the data sets have been increased at about 20% per year in this survey. And now how fast is RAM on a single server increasing? I used here a proxy. Maybe it's good, maybe it's not so good. The largest RAM you could get on an EC2 instance over the number of years. And this has increased at least 50% per year. So the increase of RAM has way outpaced the increase of the typical data set that people have been used for analytics, I think. So once we acknowledge that we are working with gigabytes of data, then R or this other commercial tools I don't like too much are pretty good in solving most of your problems. And the first problem is you need to read the data into R. And in 2009, there were all these complaints about how hard it is to read even like 2 gigabytes of data into R. It takes a day. But not anymore. Even the read-CSV is faster than there is all these other packages, and the fastest way to read it now is use the data table package. And Matt Dowley has just parallelized the fread in data table, so he told me to announce here that it will be ready soon. And also, this is like a benchmark. This company, Wise.io, open sourced a C++ library that at that time, a year ago, it was doing parallel CSV read. And the speed gain you get is because nowadays disks are fast, and the bottleneck is parsing the CSV file, so you can parallelize that. And nowadays you can read a gigabyte of data with data table in a couple of seconds. Once you read the data into R, you probably start to doing some kind of data managing, this kind of, if you work with structured data, aggregations and joins, and I was just wondering how fast you can do this in R and also in some other tools. So the other tools are traditional databases like MySQL, Postgres, like Python, Pandas, the big data systems like Spark, Impala, or Hive, and also the MPPs. So these are the columnar analytical databases, and virtually all of them, they forbid you in their license agreement to publish any performance measures, so I just call them MPP 1, 2, 3, 4. But you can ask, oh, this is videotape. Maybe you can ask me after the talk which one is which. So, oh, what the hell? It's basically Vertica, Redshift, Greenplum, and those kind of guys. So I still didn't say which one is which, so I think I'm good. And one thing and you can see that data table, it's actually very good. It's running single core, and it's one of the fastest things to do this kind of aggregation joins with 100 million records, a few gigabytes of data. The databases that are used for OLTP, like MySQL, Postgres, are like 2 orders of magnitude, or almost 3 orders of magnitude slower. So this is log scale, you can see. I didn't really advertise this too much. It's really such a toy example, I wouldn't call it a benchmark. So I was just toying around. And you can see also the big data systems are very slow. So you can put them on like 100 servers. It's not going to be very fast for this kind of data. And one thing I added to the slide last week, so there is this MapD is a database that is doing everything on GPUs, if it fits into the RAM of GPUs, and otherwise on CPU. So they just open sourced their core database product last week, so I put it here, and it's kind of off the charts. So it's really, really super fast. So this is something to look for. I always thought that columnar databases like Vertica, Redshift are like the fastest things on the planet for this kind of things, but now we have to watch out for this things running on GPUs. But of course, some people will have larger data than it will not fit in the RAM of a single server, and for those, I'm really big fan of this columnar analytical databases. It's the only non-open source product I have virtually ever used in the last 10 years. And Mike Stonebreaker here is the father of this columnar databases. So he had a research project that, and later he founded Vertica. And anyway, if you do structured data and your data is pretty big, then it should sit in a, or anyway, it should sit in a database, but if it's really big, it should probably sit in one of those analytical databases. Or you can, and you can use, so the way you can work with the data is you do this aggregates, joins, feature engineering in that database, and then you grab the data into R. So that's kind of the workflow that works for me. Or if you are this kind of Spark lover, then do the same with Spark as a backend, and then reduce your data, and then work with, from there on, with R. Once you did this data managing, probably with some visualization, you are super excited to get into modeling, and this is more realistic benchmark that I did on various open source machine learning library, and this will be in more detail in example number 2, but just kind of like peak would be that there is a huge difference in performance here as well. Sometimes 10x, but even 100x. So you would think that everyone is implementing the same algos from textbooks, like for instance, in this case, for gradient boosting machines, but still there is all this kind of performance optimizations, especially, most of it is how you access the data during the training in such a way that you keep the data as much as possible in the CPU caches, L2 cache. And the best implementations are those made by people who have this HPC, high performance computing background, and not really the ones that have the big data background. And we are super lucky, so all this is available from R with like packages like H2O or XGBoost. You can just install it from CRAN, and it works out of the box. So basically, we have all these things I've been talking about, we have them in R, or from R. But it's not always about the tools. So many times you do machine learning on some data, and that you think that by increasing, by taking more and more data, you would do better and better. But this is not always true. Typically on dense data sets, the linear models will top off in accuracy. So here is a learning curve with, so the horizontal axis is the number of data points on the log scale in millions. So you can see from 1 million to 10 million data points, the linear, the logistic regression didn't get much better. If you use random forest, you can get better. And actually, if you use random forest only on 1% of your data, you will beat someone using like a big data system, but they do linear model because that's all they have. So I think you kind of have to know what you are doing. This also goes to the joke about data scientists. So yeah, you have to know, and you have to know statistics, you have to know your assumptions. So it's not always about the tools. This is a great book for machine learning, I think. I have this kind of statistical view. I also like to do a lot of data visualization. And ultimately, you also need domain knowledge in the business you are working. If you do finance, then you need that domain knowledge. So I think I would argue that R is the best tool for doing most of this work for most of us. And distributed computing, the tools in the distributed computing, they have for now kind of little features. They don't spoil you like R. They're kind of slow and they fail very often. So you kind of have to decide where you want to spend your time. Do you want to produce value by looking at data and analyzing the data and doing modeling, or you just want to spend your time fighting the tools? So, and I'm not really against big data. A lot of companies have big data, and in a lot of companies you can get away with like ETLing, reducing this big data in something that's more refined, more clean, and more manageable, and then you can do the rest of your work on one single server. So I think your job as a quant or a data analyst or a data scientist is to create some kind of value out of data. Often this means dollars, and just use the tools that are right for the job and do it productively. Don't worry about all these blog posts about what tools you should use. So here's some kind of summary of this first part, since I didn't have too much information on the slides, but this is precisely what I've been talking about so far. And it's kind of unsexy, but basically the biggest bang for the buck is just get more RAM. So in the second example, I will ask this question, which open source tools off the shelves can we use to do binary classification on 10 million records? And this came up for me at work, so I thought I will do like a little afternoon project, and it's been a little bit more work. And why open source and why off the shelf? So there are these competitions, Kaggle's, and they did this interview with the then #1 Owen Zhang, and they asked him how does he win all these competitions? Does he implement his own machine learning algorithms? And his answer was that basically he can use open source just for that. So, and open source, especially R, has worked for me, and I think it can work for most of you as well. So this is the GitHub repo for this little benchmark. So binary classification, 10 million records. And let's see which algorithms. There are these 2 papers that have, they're from 2006 from overlapping authors, and but I don't think they're outdated. So they took more than a dozen data sets with different, they implemented a dozen algorithms for binary classification, and they used various metrics, about 10 of them, and they looked at which algo was winning how much percentage of the time, and the ones that usually come up are the same that come up in practice, the top, and also the same that come up in Kaggle. So random forest, boosted decision tree, lately GBMs, ANN, artificial neural networks, lately deep learning. Support vector machines. They don't scale linearly with the dataset size, so it's almost impossible to do it on 10 million records, so that's why I didn't look at them here. And then you always want some kind of simple logistic regression linear model for like a baseline, so I kind of look at that as well. But it's, again, not only about the models, so you need to clean your data to get good performance, you need to do this data, feature engineering, and if you really want super high performance and the last digit matters, then you need to work a lot and tune these models and also ensemble many of them. So this is virtually the only way you can win Kaggles lately. And ultimately, it's kind of work is all this data mining or data science process. So this is my view of data science in one slide. It's a rip-off of this bottom CRISP DM, which is from 1999. So there are a lot of people, they think that all this data science thing was invented in the last 3 years, but actually people have been doing this for quite a while. And open source packages, I looked for binary classification, R packages, Python scikit-learn, Vopa Wabbit for linear, H2O, XGBoost, and Spark. And I got this based on talking to friends, reading Kaggle blog posts, and Googling. And I also did a survey at the LA Machine Learning Meetup, and indeed, these are the ones that are used by most people. There are also a few commercial ones. I think MATLAB came up at 15%. That was the top used in that crowd. And all this, they promise you everything. And I was kind of wondering if all this is true, that they are like scalable and optimized and parallelized and built for scale and all this. So I took this public data set, the Airline data set, where you are supposed to predict if, you can predict if flights are delayed. And I used EC2, so it's reproducible. And I was wondering about scalability in terms of training time, memory usage, and accuracy. And so I increased the data set size. I took samples of the increasing sizes. I also looked at other things like CPU percentage, usage by core, and this kind of things to understand how they work. But basically, these are the three metrics. And this is not Kaggle, so I didn't aim for like the highest accuracy. So if AUC is close to the best, it's pretty good for me. And I just don't want this to train forever, and I want it to fit in the RAM of a single server. So the code is here, all on GitHub, with some discussions. And I used the 80-20 rule, so I aimed for 80% of results, meaning answers to my questions, with as little work as possible. So I call this benchmark kind of simple, limited, or incomplete. And the benchmarks are wrong anyway, all the benchmarks. So quickly about the linear model. In a GIST, linear models on 10 million records is super easy. You can do it in R, in a matter of seconds, with few gigabytes of RAM, even on a laptop, and all the tools work quite nicely. So linear, even on 10 million records, it's fast. It fits in RAM. It's just that it's not very accurate on this data set and on many data sets that are used in e-commerce or business. So the AUC is 0.71 or 71% on the linear models. So the first real model is random forest, and here is how much it takes to train a random forest in these tools. I'm a big fan of R. I've been using R since 2006. I actually use the random forest package. I even have it in production for some little data project. And it kind of hurts that random forest package is so slow in R. So this is the original package written in Fortran by Leo Breiman. And it seems to be kind of outdated, but it's not R to blame. So, and you can see later that you can do random forest in R using other packages, notably XGBoost or H2O. So the fastest are the one that scale the best, H2O, XGBoost. These graphs that are kind of terminated at 100,000 or a million records, it means that the tool crashed for larger data sizes. So ironically, Spark has not completed on like bigger data. And it was because it's also using like about 10 times the RAM of the other tools. So it's kind of surprising that all these people, they implement in theory the same algo, and there is so big difference between the training time among them. And accuracy-wise, also like H2 or XGBoost, again, both have R packages on CRAN, so you can use them. And Spark has this kind of accuracy problem, which I pointed it out to the Databricks guys, and they realized that they were aggregating by votes instead of probabilities, so they fixed that, and now it looks like this. But now it's still something wrong with the AUC in Spark, so you can see that it doesn't get better when you increase the data set. So ironically, Spark is for big data, but it doesn't work well on big data. And of course, they promised it's going to be faster and it's going to be using less memory. So super excited. Last year, Spark 2.0 came out. It has a really nice data frame API. So instead of doing this with like 20, 30 lines of code, now you can do it with like 3 or 4. So I really love the API. They could have looked at R, which has a data frame for a number of years. So I rewrote the code in this new API, and I was hoping that it's going to be faster, and also they will fix that bug. So ironically, it's slower, and it still had the same bug. So whenever I submit talks to this kind of vendor-run conferences, they get somehow declined, rejected, so I wonder why. But don't get me wrong, so distributed computing is very hard, especially machine learning on multiple systems is hard. If you play a little bit with hyperparameters, you can get with random forest in H2O the AUC up to like 0.8 or 80%, so you can see that you can way better than with linear. So the linear was 71. Now boosting. So GBMs are nice. You can get even better accuracy than with random forest usually, but you have to do a little bit more work and by tuning, and also you can overfit. So if you train them too much, they will overfit, so you have to do some kind of early stopping. And the scalability graphs, they look very similar to the ones at random forest. So again, the best tools, H2O, XGBoost, you can use them from R. And then R's GBM package is actually pretty good, so it's better than Python's. And it's an old package that hasn't been maintained very much lately. And it's running on single core, but it's surprisingly good. And then you can get 81 AUC with boosting. So you can beat the random forest, but you have to do a lot more work. Now deep learning. So there is this hype in the industry that we should use deep learning and GPUs, and we should call it AI, and we should use it for everything. So I tried deep learning at various data sets at work. I also tried it on this public data set. I spent days tuning. I talked to experts in the field, like the guy who wrote the deep learning package in H2O. So we simply couldn't get better accuracy, better AUC than 73 on this data set. So deep learning, I don't think, is the answer to every single machine learning problem. So it just doesn't work well on all data sets. So, and those data sets are common in practice. So it's a mix of categorical and numeric. And then the numeric, they have, some of them, they have like medium, some of them have like higher cardinality. And it seems like just these ensembles of trees, like random forest and boosting, they are better in dividing your space, slicing your space, and doing predictions rather than the neural networks, no matter how deep they are. But many people will say, oh, but my data, I have bigger data. So I try to satisfy them a little bit. So let's create some big data if we don't have. And of course, in the next experiments, I don't look at AUC because it's just the same data is replicated many times. So it's not going to increase the AUC, but I still can use it to see how fast and how much memory those tools are using. So 100 million records, you still can do it decently in R with a GLMNet package, but probably at this point you better use something like H2O VOPA-WOBIT. And if you have 1 billion records, you still do logistic regression. H2O is like 10 minutes, 100 gigabytes, still on one single server. VOPA-WOBIT is also pretty decent, so 1 billion records. If you want to do this more CPU-intensive things, then random forest GBM would take hours on one single server, 100 million records. If you absolutely want to do distributed, you can do. H2O is basically a distributed machine learning system, open source. Again, you can drive it from R. You can run it on 5 nodes. The logistic regression is going to get almost like 5 times as fast, but the random forest, for example, is not. And it's because it's spending a lot of time sending data between the nodes. And this is one of the main problems with distributed computing, that the communication can slow down, and actually you're not going to get faster, or it depends on the data. So in summary, I think that our job as quants, analysts, data scientists is to do some kind of critical thinking and also do quantitative measurements. And I think this has worked really well in solving and optimizing a lot of business problems and even in finance. And I just want to shed light that we should do the same on our own work. So we should look at our tools critically and quantitatively, and also at our work, and we should just not believe the hype on the latest blog posts over the internet. So I think that's pretty much what I have for now, and we can open for questions. Here's my contact if you want to reach out in the break to me, or you can reach me out. I suggest email. So thank you very much.
Stunned silence. Questions?
Probably it was so trivial to everyone that just pretty much everyone agreed. Yes?
In your comparisons with,
Yeah.
with Python, what packages did you use? Like you used HDBoost and H2O for R. Did you use any comparable packages for Python?
Yeah. So Python, what's nice in Python is that there is the scikit-learn, which is kind of like a unified API to a lot of packages. So whenever here is Python, is the scikit-learn. They have random forest, they have gradient boosting, they have logistic regression is just based on the lib SVM and lib linear packages. But ultimately, everything is like facade to C++ or maybe Java. All the libraries. And nowadays, everyone makes it available from R and Python because that's what people are using. Right. Yes?
Are there still domains where the commercial packages dominate the open source in abilities and performance?
I don't think so. I'm probably not the best person to answer this question since I have been using R since 2006. But actually, I moved from MATLAB to R, and I remember exactly that I moved because I wanted to work with categorical data, and MATLAB didn't have data frames, and R was already at least as good, I think, as MATLAB overall, and it had data frames, so I just moved to R. And I talk to people like at SAS and other companies, and yeah, they have relatively high performant machine learning algorithms, but they're not, actually SAS, someone submitted some results, so you can go to my GitHub and he submitted some results. It was a little bit slower than the best open source packages. So it's definitely not better. Yes?
Was your data set structured or unstructured data? Did that have
Yeah, I work most of the time with structured data, so, and for the modeling, you would have to structure it anyway. So ultimately, for this kind of typical machine learning, binary classification, or regression, you would create a data matrix. And I would argue that for most companies, the data matrix fits in the RAM of a single server. So you might use some big data system to ETL your data into this data matrix for modeling, and then just use R on a single server and this high-performant machine learning packages.
Case in point, to link it to the previous presentation, I mean, there was millions of emails in the Enron corpus, and on the slide summarizing the regressions, number of observation at the bottom was 81. Take your pick whether that's big data or not. I mean, because that's unstructured data, but once you condense it to do something that's analyzable, I mean, it's hard, I guess. I mean, that's a panel time series problem, maybe. It's just domain knowledge, as we said.
All right, thank you very much again.